First, we will look at the one-dimensional Euclidean distance transform algorithm before moving on to its work-time efficient implementation. The input is a discrete array of pixels where foreground pixels are represented with 1 and background as 0. The expected output is the distance for each pixel to the nearest foreground pixel. A serial implementation of the Euclidean distance transform is as follows. The distance at each foreground pixel is initialized to 0 and for all other pixels is initialized to infinite distance. We then have a forward pass through every pixel where the distance is calculated as the minimum of the current pixel distance and the immediate previous neighbor plus 1. This results in the distance to the closest left pixel being known at every pixel where it exists. There is then a backward pass through the data which performs the same calculation, but the result will now be the closest distance to the nearest foreground pixel, whether it is to the left or the right. The closest point problem is very similar, but in this case we aim to find the index of the closest foreground pixel for every input pixel. From the known closest point, we can calculate trivially the Euclidean distance for each pixel. Here we see how to compute the closest point using warp voting instructions. We will assume there are 32 threads in a warp. Each thread will set a Boolean variable to true if it determines it is a foreground pixel and false otherwise. The threads will all execute the ballot function on that variable to obtain a 32-bit integer representing the status of each of the 32 pixels. Each thread will determine its closest left neighbor. The count leading zeros instruction counts the number of most significant bits that are 0. We can define a function left that will find the index of the most significant 1 bit of an integer. If the input integer is 0, count leading zeros returns 32 and our left function returns -1. Here we show an example. Each thread operates on the same integer input x. Each thread creates a mask of 1 bit up to and including its own bit as depicted for the first 7 threads here. The mask is ANDed with the integer input and the left function is operated on this result. In this case, thread 0 has no left neighbor. The AND operator applied to the mask of thread 1 and the input also results in 0. Thread 1 also has no left neighbor. If we apply the same operation to threads 2, 3, and 4, we obtain the same result. For thread 5, the AND of the mask and the input result in a 1 bit at bit 5. The left function returns 5 for thread 5 and also the same for thread 6. Also, here are further example threads. Each thread correctly obtains its closest left neighbor or itself using these instructions. We can use the findFirstSet function to find the index of the least significant 1 bit of an integer. Using this, we can define a right function which returns the correct bit position, which we can use in a similar way to find the closest right neighbor for each pixel. Here are some example threads. In this case, the mask is from the current bit up to the end of the warp. ANDing the mask with the input x and applying the right function correctly identifies the index of the closest right pixel. At this stage we have the left and right output. The absolute value of the left minus the index position gives us the distance to the closest left pixel. Similarly for the right pixel. By taking the minimum of those two, we obtain the Euclidean distance to the closest foreground pixel within the warp. The previous approach requires 2 passes through the warp. We can improve on this with a 1-pass algorithm. We modify the mask so that the left function returns strictly the closest left neighbour, not including the current pixel. The previous mask for thread 17 is shown with the mask in this approach underneath. The left function returns 12. Thread 12 previously returned 12 itself, but with this mask it returns 5. Each thread writes the result of the left function to an array Ln, which is the index of its nearest left neighbour. Each thread will then check if it's a foreground pixel, and if so, it will check the Ln array at its index position. If the Ln array has infinity, which will occur for only one foreground pixel, that thread will write its index to the first position of Rn. Otherwise, it gets the position I of its closest left neighbour from the Ln array and writes its thread number to the Rn array at position I. For example, foreground pixel 12 will get I equals 5 from the Ln position 12 and write its thread number 12 at Rn 5. Foreground pixel 22 will get I equals 12 from the Ln array and write its thread number 22 at position 12 in the Rn array. Foreground pixel 5 sees infinity in the Ln array at position 5, so it writes its position 5 at Rn 0. Using these arrays, we can now obtain the closest point for each pixel. Each thread will check if it's a foreground pixel, and if so, it will write its thread number to the closest point array. Otherwise, the closest point is either the closest left point or the closest right point. The closest left point is obtained from the Ln array at the position of the thread index. The closest right point is found by getting the closest left neighbour from the Ln array for that thread. If that is infinity, then the closest right neighbour is given by the first position in the Rn array. For all other values, the closest right pixel is found by looking up the Rn array at the position given by the Ln array. These 2 points can be compared to see which is the closer, and the Euclidean distance can be derived from the closest point. We can compute the left closest point in order 1 in a warp. This part will show how the closest point is passed to all pixels. We use a reduction phase and downsweep phase to pass information to all pixels. In the reduction phase, we start with n over 32 warps. At each iteration, we reduce the number of active warps by a factor of 32. The height of the tree is therefore log to the base 32 of n, which is the time complexity of the algorithm. We use at most n warps. For this example, we assume a warp size of 4. If we run the left closest point operation on each of the 8 warps at the leaves of the tree, we get this situation. The rightmost element of each warp then has the same operation applied, given the next level of the tree. This continues until we reach the root of the tree. That information is propagated in the downsweep. Information in the head is passed down to the next level of the tree. No action is taken at the leftmost nodes, which are denoted as empty in the paper. At the next level of the tree, the leftmost pixel is passed to the remaining pixels. For both phases, the trees are height log to the base warp size of n, and at most n warps are used in each phase. This leads to order n work and order log n time complexity for the 1D closest point problem. We will now derive the parallel algorithm for the two-dimensional Euclidean distance transform. The first stage is to use the 1D Euclidean distance transform in each column to provide every pixel in the 2D image with its closest point within that column. An example is given in the figure. Each pixel in the row will now know its closest point in the column, labelled C1 to C8. For every pixel on the row, its closest point will be one of those closest points. Now consider the Voronoi diagram. It is clear that points C2, C3, C6 and C8 cannot be the closest sites for any of the pixels on that row because the Voronoi cell of those sites does not intersect the row. The aim of this algorithm is to eliminate those sites from the closest point computation efficiently and in parallel. First, we consider the rejection criteria for the sites. For any three consecutive Voronoi sites, we find the two consecutive perpendicular bisector lines as shown. These lines will intersect with the row J with coordinates u and v. As shown in the left diagram, for B to be closest to points on J, u must be less than v. If, as in the right diagram, the intersections with the row are the other way round, then B cannot be the closest site for points on J and it can be deleted. Also, since we are dealing with pixels at integer locations, B also cannot be a closest site if the intersections of the perpendicular bisector lines fall between two pixels or exactly on a pixel. Therefore, we can delete a site if the floor or ceiling of u and v are equal. Therefore, we can remove a site B if the floor of u is greater than or equal to the floor of v. In the example so far, the points have been all above the line. The rejection criteria are still valid for points above or below the line. Here are some examples to demonstrate the criteria are still valid in this situation. Each site can impact an interval along the row. These intervals are in the same order as the sites. We will divide the work of calculating which sites have intervals on the row amongst processors, then merge the resulting lists. During merge, some sites will no longer have an interval on the row, so these are removed. During merge, we will add a point from one list to the previous list, but we apply the rejection procedure to the top of the list to see if by adding points we can remove those sites. We continue recursively until we can no longer remove sites from the first list. If two sites are added from the second list, we can add all the remaining sites without further rejection. See the paper for details. There can be at most n sites on a row. Divide these sites up into lists of k sites. Apply the rejection procedure at each processor. Merge two consecutive lists using the merge procedure. Keep merging lists until we have just one list of the closest sites for a row. The merge tree has log n height, and since at most n sites can be removed from the candidates, there is order n work. Once we have the list of sites, we calculate the intersection between the row and each of the perpendicular bisectors between consecutive sites. Here, the perpendicular bisector between C1 and C4 intersects at x equals 2 once we've rounded down. The left site is C1 with coordinates I1, J1. Therefore, I1, J1 is written to position 2 in the array. The array has the remaining sites distributed according to the perpendicular bisectors. We then fill in the remaining points using the right side closest point solution. Finally, we can calculate the distance from each pixel to its closest site as indicated by the list. Further GPU implementation details are in the paper.